Let us begin. So I'm Christian Huebner. I am Director of Services Architecture at Mirantis and also at the same time storage subject matter expert. I am working on pretty much any storage project that we have, and as you probably all know very well, pretty much every OpenStack Kubernetes project has a storage component to it. Today, I would like to walk you through the current state of storage in OpenStack, what you can do, how you can do it, what to consider when building a storage environment for your OpenStack Cloud.
Considering a cloud transformation or migration? Check out the Total Guide to Private Cloud from Mirantis to learn how open source cloud on-prem gives you cloud benefits without the downsides. Download now at mirantis.com/privatecloud.
I just thought I would start with a couple of fun facts. In the beginning, the very first hard disk was an IBM Ramac 350 from 1956. It was 5 megabytes in size, could do 8.8 kilobytes per second, and it weighed almost a ton. Nowadays, the largest readily available storage device, single storage device, is a 30 terabyte NVMe, 6 million times the capacity, 875,000 times the throughput. So we have come a long way in storage, and still storage is one of the major components that make or break your cloud experience, hence the title Make or Break. I have seen in my 10 years at Mirantis that successful storage projects, less successful storage projects, we have identified the factors on the less successful storage projects. And in the end, what it comes down to is storage needs to be considered. These quotes on the left side that you see here are all quotes that I was actually told by customers. Things like, it's there and it works. Seems to be a common theme. There's a lot of people who think that way. Yeah, that somebody built it, I'm using it, and as long as it works, I'm not going to complain about it. Of course, also, I never really thought about it. And I cannot really blame people because everyone is talking about networking, everyone is talking about the cloud itself, but nobody really thinks that unless you have a solid base underneath your cloud, the cloud is not going to do anything useful. In the end, data is at the core of everything, any business we conduct today, and we need to make sure that we keep the data safe, that we have enough performance to make the storage subsystem useful for you, that you are not creating a bottleneck, and most important of all, that you are not going to run in a situation of catastrophic failure that you cannot recover from, because this has in the past killed businesses. Where to keep your bits? We have different ways of attaching storage to an OpenStack cloud. OpenStack has its preferred methodologies for attaching storage. One of them, the most common one, is software-defined storage. In this case, it's usually Ceph, which has been developed in lockstep with OpenStack. This was from the very beginning was the idea to have it in OpenStack. But in the more recent years, the other storage subsystems have become a lot more prevalent. Things like Pure Storage, Lightbits, Dell PowerStore. There's a lot of storage subsystems. I don't want to insult anyone by not naming the storage subsystem, but they, in the end, there's a lot of choice. Companies have their preferred vendors. They want to have their storage in their cloud, and we are going to look at how this can be done. Network attached storage is a bit of the same. NAS is essentially simulates in an OpenStack environment, simulates mounted local drives. And then finally, object storage, which is not, it is very important for applications but it is not really a storage subsystem that can be standalone for OpenStack. So how does OpenStack store data? First of all, we have image storage. Image is very important because this is pretty much any virtual machine that you're building is built from an image. And these images are kept in the OpenStack Glance component, and they must be transferred to the actual active storage for OpenStack to be useful to so you can actually launch instances. There's two different block storage types in OpenStack. One of them is ephemeral block storage. This is kind of oftentimes dismissed. This is what you boot what you boot instances from. But in many cases, people do not use ephemeral storage, even though it would be beneficial for them. Especially, there's a lot of customers who started just booting from volume, and this is not always in your best interest. So persistent storage, especially if you have expensive, high-performance persistent storage, there should be reserved really for your application data, where your performance is actually useful to you. If you take an instance and you boot it, the amount of data that goes in and out of your boot storage is comparatively small. This is so if you are, let's say, you have a 40 gigabyte boot drive and you have a 100 gigabyte persistent storage drive, then you can use the persistent storage for only your application data. The boot storage drive does not have to be quite that fast, and it can be another different storage subsystem. So the big difference between ephemeral storage and persistent storage is how long the storage volume lives. In ephemeral storage, when you destroy the virtual machine, not when you reboot it, only when you destroy the virtual machine, the data dies with it. So for an operating system, that really doesn't matter, because when you create a new instance, then it will be rebuilt from an image, and you are going to be back to where you originally started. Persistent storage, the volume is a standalone. It can be attached to anything you wanted to attach. You want to attach it to. For instance, you want to move it to a different instance. Then you basically just detach it from one instance, and then you add it to the other instance. So everything that cannot be easily recreated should be on persistent storage. If you want to build storage subsystem with different persistent storage backends, you can do so. It is possible to have, for instance, something that is storing data on an NVMe SAN, and as an alternative, Ceph volumes that are cheap. And as another alternative, you could even have something built on NFS or something. Furthermore, and this is something that I've seen time and again in projects, one of the most underutilized storage systems is backup. Cloud storage, tape storage, archival grade disk. A common approach seems to be, well, we are using RAID or we are using replication. Why would we use backup? Two entirely different things. If you're using RAID, or even if you're using replication, what you mostly protect yourself about is device failure. So if you have a dead storage device, you want to make sure that you can keep going while that storage device is being replaced, or until that storage device is being replaced. Hence, you have a RAID or you have replication. If you have something else happen, let's say you have catastrophic failure, or even worse, if you have an insidious failure, for instance, let's say a bad actor makes changes to your environment. Could be something as obvious as ransomware attack, or it could be something as insidious as somebody just changing a couple of numbers in a spreadsheet. So how do you recover those with the RAID or with replication? If you're trying to do this, you will notice that all the replicas or the RAID itself is just taking the bad data just as willingly as it takes good data. So you have to get the data back from something. The most simple way to do this is to have snapshots. So you would have, for instance, a snapshot from 24 hours ago. And if you see a ransomware attack happen, you could conceivably just recover from that. What happens if you only notice after, let's say, 2 weeks or 3 weeks that your spreadsheet contains the wrong numbers? The only way to get this back is if you have some sort of backup, and that backup should ideally not be connected to your environment before or during the normal business operation. It should only be available when the backup is actually being done. And it should be stored offsite in case of absolutely catastrophic failure. Let's say your data center gets flooded. Let's start with storage backends. First of all, I would like to talk about Ceph. I've heard a couple of not so complimentary things about it that usually have to do with the complexity and with the amount of effort needed to make it work. A lot of this stems from the early days of Ceph, where it really was pretty difficult to deal with. Nowadays, this is not the case anymore. But if you're using Mirantis Mosque, for instance, everything, the whole Ceph cluster, everything is managed for you. There is nothing that you really need to know about how to operate it. It just works, like we had a couple of slides ago. Also, I have had in the past a customer who did their level best to try to destroy the Ceph cluster in a bunch of really creative ways, like experimenting in production. And they interestingly never managed to actually lose data with it. We had a couple of times where there were server outages, where there was storage devices that were destroyed, but we had actually, Ceph was resilient enough to survive all these. And there's one thing that Ceph can do that is not very common in storage backends. There are some SANs that theoretically can do it, but we have not actually played with that, which is copy on write. If you, as I said before, when you transfer or when you launch an instance, you have to transfer the image to the active storage for the instance and create a volume from it. In Ceph, that is not quite true. In Ceph, the image stays where it is, and then it will be only an empty image is created on the active storage, which is the volume that is attached to your instance. And this is an overlay to that image. And every time you change something in that image, let's say you edit the hosts file and you add something, you add a host and an IP address to the hosts file. That is written into that empty volume and supersedes the hosts file that is in the original, in the image. But normally, when you have operating system drives that do not at the same time have business data on it, we have found that the deviations from the image to the respective instances or their overlay stores is a few percent, something between 2 and 5-6%. So this is actually one of the most efficient ways to deduplicate data. So you simply don't write anything duplicate. And the other thing is, and this is also an example from a customer here, they had images that were almost a terabyte in size because they contained Windows, they contained a complete source tree for the application, and they contained a bunch of other components so that the image itself was 800 gigabytes in size. The downside to that is if you want to copy this, you will have to pump this all. If you start instances, you have to pump this over the network time and time again to initiate the instance. With copy on write, the instance comes up in seconds, possibly even faster than that. Typically, the boot time of the instance is much longer than the create time. So this is what an OpenStack Cloud with Ceph looks like. You have OpenStack. In our case, we are using Mosque. This is an OpenStack. We could call it a distribution that has, in addition to OpenStack, our lifecycle management and our monitoring subsystem. but in the end, it is mostly just plain OpenStack. So you have Nova, which is a compute component, and that uses the Ceph cluster, that uses pools in the Ceph cluster for virtual machines. You have Glance. This is the persistent storage component. You have Glance, that is the image storage component, stores images in Ceph, which is what makes it possible for us to essentially attach empty volumes in the VMs pool to the images in the images pool, and then initiate copy on write. We have Cinder, which is also using RBD. RBD is Rado's block device, and is using a volumes pool in the Ceph cluster. The Ceph cluster separates everything, all the storage types, all the storage buckets in different pools. So you have in a Ceph cluster, you can have different storage types. You can, for instance, see the object store is in the same Ceph cluster, and it even shares the same storage devices. And the only difference is that the data is managed in a different pool. So what about other SDS environments? You could have Dell PowerFlex, you could have Scality, you could have Lightbits. There's a lot of other software-defined storage environments that we are talking with. There's also Portworx. In any case, typically those are not unlike Ceph. They are proprietary, or oftentimes proprietary environments that look like, if you take the lid off, there are not really that many ways to replicate data and to build a software-defined storage subsystem. So the architectures are all pretty much the same. You have devices in either compute nodes, or you have the devices in separate nodes, and they are in some way aggregated together to become software-defined storage. What is common to all software-defined storage systems, by the way, also including Ceph, is that it is necessary to have local drivers on all compute nodes. You have the compute node when it in a software-defined storage system essentially becomes part of the cluster. It has a driver, and the driver speaks the protocol that the SDS needs. And the integration, how well it integrates with OpenStack depends on the driver capabilities of the respective SDS environment. The next is probably the most well-known here. Everyone knows what a SAN is. It is essentially a conglomerate of disks that are typically organized in RAID groups. If you have different RAID types for different data protection mechanisms, something like a RAID 1 mirror, a RAID 0 striping, a RAID 5 or 6, or RAID Z, that would be some sort of essentially erasure coding. Yeah, it's not called that, but it is the same thing. You are creating additional data to protect the data that you have. SANs can be very fast. They are not necessarily so. You can have anything from hard disk-based SANs to NVMe-based SANs. They can be quite fast. They can be faster than a Ceph cluster, but they have a number of downsides, to one of them being that the data path from the compute nodes to the SAN is not as, let's say, broad as it is to a Ceph cluster, because in Ceph the virtual machines can directly talk to the Ceph node that has the actual, and the object storage daemon that has the actual data. So if you have only a few data requesters at the same time, you won't see a difference. But if you have very, very many data requesters, at some point you will hit the capacity limitation of the SAN gateway, essentially, and so you will potentially create a bottleneck there. So typically with the SANs, I have seen that there are some that do something similar to copy on write, but typically with a SAN, the instances require that the image is copied to the data store and is so you have the added capacity and a performance or startup time gap. Shared file systems, NFS, so essentially, I mean, it has the same disadvantages that the SAN has. It is also centralized. It also has only a limited capacity, throughput capacity in the, let's say, filer heads, whatever you have, NetApp calls them filer heads. And so they can also be relatively fast, but the downside to them, the additional downside to them is that you need to mount an NFS locally to use it as OpenStack backend storage. It does not have, there is no component that actually allows you to just mount the share. You basically have to mount the shared file system and then put all the images in there. Local flash storage. This was, by the way, I'm just noticing that this was missing at my where do we store data sheet earlier on. Local flash storage is becoming rather a favorite of people who are really chasing after speed. Even the fastest SAN has a throughput limitation at some point, and local flash storage really was only limited by the device speed itself. The downside, or let's say the flip side to this is the third item from the bottom, is that the resources are often not utilized very well. If you're using the flash storage as a backend to the ephemeral storage, which is the most common way to do it, because OpenStack's implementation of persistent storage on local storage is, let's say, a little bit dicey. Then you will see that you may have on one system, you may run out of compute capacity and memory capacity, but you will have plenty of storage. And another system, you will have enough compute and but not enough storage, depending on how big or small the storage devices that are attached to the instances on this node are. So you have to have enough capacity to make sure that you're not running out of storage on any of the nodes. And in the end, you will probably find that the capacity is that you have to overspec to make it work. The other thing is, and this is something that we have not discussed before either, there is no true live migration. Local storage is local storage. If you want to live migrate from one node to another node, then you have to have shared storage. And this is not the case with local flash storage. So the live migration, there is still a way to do live migration in quote marks, but there is going to be a gap. It's not going to be instantaneous like it would be with other storage subsystems. And in the end, if you cannot actually make use of all those IOPS or all that throughput, and in most cases you really can't. It's doing the math of how much your virtual machines or instances how many IOPS they can consume. You'll find that what the modern NVMe storage devices can provide is not a ton more than you can actually consume. And performance is in most cases is not really enough of a benefit in this to ensure or to choose local flash storage. I would only be very careful with this. For some cases it makes sense, but not for very many. What about combining storage? We have one of the most common, in our experience, one of the most common combinations is Ceph for ephemeral and for image storage. So you can make use of copy on write, and then using a SAN as persistent storage, something like a flash SAN from one of the many manufacturers. The This is probably also possible with other SDS, but we have had very little requests. We have had one request for Dell Power Store in a recent future and one for Lightbits. So the most common storage subsystem that we see are various types of SAN. Fiber channel, iSCSI, flash, but in the end, it's mostly SANs. So the other one would be Ceph and local NVMe. For instance, if you want to have a couple of very fast nodes, something like GPU nodes, and you need fast local storage for these, you can still have a Ceph cluster, and you can have a local NVMe for these few nodes where you actually can consume the performance envelope. What do you do if you don't want a Ceph cluster at all? We have some customers who do not want Ceph for a variety of reasons, but in this case, clients would typically be using Cinder as a backend, not any storage subsystem, but Cinder OpenStack persistent storage, and through that Cinder backend, it would be stored on that third-party SAN that we are using. And Nova either can have no backend at all. It's possible. In this case, you would not be able to create either boot storage or ephemeral storage through Nova, but you would be able to boot from volume. You would have an image on Cinder, and then you would boot from the volume that's also on Cinder. Or you could have local file system on the compute nodes. What do we do? This is one of the most important considerations, and I have had customers ask me, why are you always talking about failure? Because failure is what kills you. As long as everything runs, everything is nice. We don't have any problems, and we can of course hope that that something is not going to happen. But quite honestly, I would not bet my business on it. So what failure scenarios do we most often see? The most common, of course, is a device failure. Dead SSD, dead hard disk, sometimes a dead node. This is something that should be easily repairable. If you have software-defined storage, you replace the device. If you have a SAN, you also replace the device. You have replication or RAID groups to make the device replacement invisible to everyone. Much less common, but also I have seen it happen as rack failure, specifically power failure or switch failure, especially with customers who only use one top of rack switch, which still exists. So if you have a whole rack fail, that may become a different kind of problem. For instance, if you are using, if a rack fails that has a storage device in it, let's say something like a SAN, a smaller SAN, that is limited to one specific rack and is not distributing data across multiple racks. In this case, you would potentially be out the data until you repair that rack. What else? Software, we have bugs, functionality gaps, things that, let's say, for instance, something crashes your storage subsystem or crashes components of your storage subsystem. And then you have the human factor, which is either human error, somebody erasing something they should not have erased, which we have also seen, and bad actors, of course, both inside your company and outside the company. And somehow, of course, when failures like this has occurred, regardless of what failure, you have to recover from that failure. Recovery from device failure is pretty easy, normally, as long as you still have enough redundancy left. So if you lose, for instance, if you lose in a RAID 5, you lose 2 devices, then you will lose the data on that RAID 5. If you're losing in Ceph, if you're losing all 3 replicas of something, then you will lose that data. The difference is that the RAID is typically within one box. So if that box dies, you are losing all even your redundancy through the RAID. in software-defined storage, and this is not specific to Ceph, this is in any software-defined storage that you have, that you may have. The redundancy is typically across devices. So you may have, let's say, 3 devices, one of which is in each of your racks. So even if that whole rack fails, you're only using one of your replicas, and you can continue on with 2 more replicas. So that's a consideration worth thinking about. Now, the next thing is recovery from catastrophic failure. Fire in a data center, you have flood, you have an aircraft falls on your data center, whatever can do catastrophic damage to your environment. There's 2 components to this. First of all, of course, you should have backups. And you should not store your backups on site. So if you are doing backup through tape, the data should be transferred to some facility to store that. There's also the option to do multi-site designs. Multi-site designs are not only important to have some survivability of, let's say, fire in a data center, they're also important for recovery. So if you do not have a multi-site environment, and you lose, let's say, the data center that has all your eggs in that one basket, then you do not have another place to start that up again. Even if you have a good backup, you will first have to have enough capacity, let's say a viable OpenStack Cloud with enough capacity in another data center to get that started again. Which is why we have quite some customers who are interested in the designs where we have storage in multiple places that can be accessed across the gap, or a stretch cluster across multiple storage entities. One special thing about this is that if you have something that replicates, you should have the appropriate number of separate places. Let's say you have 2 data centers. One of them has enough storage for 2 replicas of your data, and one has only 1 replica of your data. Then if you lose the dominant data center, you will also lose the storage quorum in that sense. And you will not be able to write until the whole thing is fixed. So if you have 3 data centers, they have to have very fast backbones. But if you have 3 separate data centers or 3 separate rooms in your data center, then you can lose any one of them, and the cluster will continue working just the way that it did before. The downside to this, of course, is that with any network-based storage that is not local to your environment, you are going to incur a performance penalty. And then the last thing is recovery from insidious failure. That is any kind of failure that you cannot immediately recognize. One of them, the most famous of them, is ransomware, of course. So if you only notice, like after a certain amount of time that your data is all encrypted, you have to have enough back data far enough back that you can overwrite that ransomware adult storage that is not of no use to you anymore unless you pay a bad actor a lot of money. So what can be done in most of the storage subsystems, this works with SANs, it works with software-defined storage. It also works with NFS. But the only storage subsystem that it does not work with is any kind of local storage. If you only have local storage, the snapshots are typically useless to you for this kind of failure. So imagine you're having a storage device that is flips a bit. You have some important file, some important volume, and suddenly a bit flip occurs and something of value gets lost. If you have any kind of mirroring, you suddenly have 2 different copies. And that is a problem because you do not know which one is a good copy. So if you have a mirror, you cannot decide which one is the good copy. If you have replication, like in most software-defined storage systems, you do know which one is the bad copy because you have two copies that are the same and the third copy that is not. So RAID is good at protecting you from device failure if you know which device is the bad one. In most cases, that's the case, but it is in the rare cases that it's not. It is a better way to protect your data is to replicate it versus doing like a RAID one. And then finally, of course, the principle of least access is of importance. So if you are doing your identity and access management design right, you can minimize the risk that you have a bad actor inside who can destroy all your data. Some operational considerations. First of all, keep the environment as simple as possible. We have had customers, for instance, in software-defined storage, who have an elaborate design of 5 different storage nodes that have 5 different configurations, this and that. It can have its advantages if you have really a use case for it, but in most cases, it is uniformity is your friend. Uniformity is what what minimizes the risk that device failure is going to hurt you. It minimizes the risk that some catastrophic failure is going to take you offline. Next step: keep your data safe. You should have appropriate redundancy for everything. There may be some data that's scratched that has no business value, but in most cases, data has business value, and there needs to be some sort of redundancy. So the design of this redundancy depends very much on what the data is, what the properties of it are. For instance, if you have anything that needs to calculate additional data, let's say, in the simplest case, it's a RAID, but more often something like ephemeral storage also, where there's math involved to create additional data for your checksums, then you will have you will lose performance associated with this. The writes are going to be slower. For instance, if you're looking at a RAID 6 versus a RAID 1, a RAID with 2 parity bits versus a RAID, a mirror is going to write a lot faster than that RAID 6 is typically. So if you have high performance requirements, that may be a consideration. Monitoring is also very important. And I see time and again, I see customers that have that devices sitting in their storage subsystem for days or weeks on end. And this is really not good. You should, whenever something happens to your cluster, you should be back to your normal state as fast as humanly possible. The risk increases with the length of the downtime. Then backups and offsite storage. Backups have fallen out of fashion, but in my opinion, backups for critical business data are still necessary. And this is where another component comes in. If you have different storage backends, for instance, you have one storage backend that is specifically for critical business data, but is only 10% of your capacity, then you can back that up much easier than if you have only one storage backend and this is essentially 100% of your data, and you have to back up everything to make sure that you are not leaving out anything important. And then the duration of recovery. When you are losing a storage device and that storage device happened to be a hard disk, it takes quite a while. If you've tried it out, you know that. With modern hard disks, with high capacity and performance being barely any better than the low capacity drives from like 5-10 years ago, then you will see that it takes oftentimes days or more to recover your data from a failed device. And during that time, of course, let's say you have a RAID 5 and you're losing one storage device, and you are exposed until the data is recovered. Future proofing. This is the final step, and I have seen that time and again, specifically in the SAN field. There are cheap SANs that are built specifically. They only have a specific capacity, and they cannot scale any farther, or they can only scale to a relatively small degree. The downside to this is that if you are exceeding this, you have to move your data to a larger device, or you have to add another device, which adds complexity again. And so it makes sense from the beginning to think about how far you want to scale, and whether this is going to be, whether what you are buying is going to be the right device for your purpose. And then the last one, I always wish I would not have to mention this anymore, but I have seen it so many times. I've seen consumer-grade SSDs in storage arrays. I've seen consumer-grade SSDs in Ceph clusters. I've seen consumer-grade hard disks in Ceph clusters, and first of all, green hard disks in Ceph clusters that have that shut down and start up when they are not in use. And the result is typically catastrophic, both from a performance standpoint and from a data protection standpoint. Every device that's bought, especially spare devices or replacement devices for an array that you do not have a service contract for anymore, it still must be enterprise grade. A recommendation for you is what should you ask yourself when you're building a storage environment? The very first of is list all the use cases that you have. Do you have anything that requires high performance? How much of your storage requires high performance? Do you have to have something for a special enterprise for special data that is mission critical for you? And list all those cases, and then think about how can you best translate this into a storage environment. How much capacity do I really need? This is one of the easier ones. You can typically say, okay, my historic growth is 25% a year. So today I have 100 terabytes. Next year I'm going to have 125. The year after I have 150 or 160. 62, whatever. But in any case, this is something that can be calculated. The next one, not so much how much performance can I consume. This is something that requires a bit of estimation and consideration, but typically your software engineers that are managing your applications can give you an insight into what they require. And it's not only IOPS. IOPS is the most visible one. This is what everyone measures. The most important piece is typically latency. So the question is this subsystem that I'm buying fast enough to, or the low latency enough to allow my databases to run properly? And is it fast enough to not lose performance because I hit the IOPS limit? So this is a question that you should definitely also ask yourself, but it's more difficult to answer it. Will I scale out? This kind of matches how much capacity do I need, but it is aimed a little bit at what can you do in the future. If you buy small devices, scaling out is a lot more difficult than if you are buying bigger devices to start with. And then is more complexity worth it? If you have, let's say, 3 storage backends for 3 different purposes, there should actually be 3 purposes for those. If you just have some storage backend sitting around, it typically makes more sense to standardize on one and not go through the complexity of having multiple different ones with different properties and having a storage backend or a storage landscape that is difficult to manage and difficult to maintain. And then one more warning that is not on here that is rather important. I have been asked time and again, yeah, we have money right now, what should we, how big should we buy? Can we build something with a petabyte? We only have 150 terabytes now, but we do not want storage, or we want storage for the next 10 years. My recommendation is universally the same. Build something that is going to serve you for 3 to 5 years maximum, because in 5 years, everything that is going to be in your storage subsystem is going to be outdated. So building something for a lot of growth for a long time is not in your best interest. I hope that was useful to you. I hope that it shed a little bit of light into what you can do with OpenStack storage. If you would like to contact me, you can use my team's services address, because it is better if it's not just ends up in my mailbox. And I wish everyone a nice evening. For the people in Europe, I wish everyone in the United States a good day, and hopefully you are going to be successful with all your storage endeavors.